Hi everyone, and welcome to another mini course of Physics Latam. Today we are happy to start a mini course on algebraic topology in physics. This is the first out of 5 lectures, and we are very happy to have ICTP faculty, Professor Pavel Putrov. He received his PhD from the University of Geneva and complete some postdoctoral research at Caltech and Princeton University at IIS. Putrov specializes in mathematical physics, quantum field theory, and low-dimensional topology. Please do not hesitate if you have any questions during the lecture. And now I'll leave you with Pavel. Please go ahead.
Yeah, thank you for the introduction and inviting me to give this course. Yeah, I'm very sorry about this technical difficulty. I thought I checked it worked from, but somehow I keep disconnected when I start screen sharing my screen. So my course, this will be a course on algebraic topology and physics. And okay, so let me kind of mention a tentative plan of this course. So I will start with some sort of motivation. And then I will give a kind of a brief informal review of algebraic topology concepts like homotopy and homology and cohomology. So this part may be, for those who are kind of familiar already with some algebraic topology, this part could be a bit boring. So then I will consider kind of some more particular applications in physics. So I mentioned something about classification and standard kind of very classical use of algebraic topology of classification of gauge field configurations. Then I will tell about discrete gauge series, also known as dash graphite topological quantum field series. And then I will talk something about classification of invertible series using logarithms. And maybe if there is some time left, at the end I will also mention something about classification of supersymmetric quantum field series in terms of generalized homology series like real chaos theory and topological model points. But this is maybe we're not going to mention this.
If there is any question on the chat, I will let you know. Okay.
Okay, thank you.
No problem.
Okay, and okay, so let me start with some motivation. So what is kind of algebra and kind of general review? What is algebraic topology? What do we mean by algebraic topology in physics? So okay, algebraic topology is kind of very roughly it concerns kind of associating kind of relation between topological spaces and some sort of algebraic objects like groups, algebra, rings, and so on. And roughly speaking, kind of, we want to study some sort of assignment from topological spaces to kind of some algebraic objects like groups, and kind of here in our course, what we will mean by physics? By physics, we mostly mean, well, the kind of fundamental theory which describes interaction, which is a quantum field theory. It's also, we know that the quantum field theory is used, for example, for effective description of some kind of quantum condensed matter systems. So why kind of what is the one can ask like why do we need why do we kind of why this algebraic topology can be useful for physics? Well, it could be useful if we have some sort of topology, non-trivial topological spaces appearing in our physics context. So what is the possible topological spaces which appear in the physics context? One, of course, very basic example one can think of is space-time. The topological space is our space-time. Okay, in principle, in practice, we don't really kind of observe any non-trivial topological spaces, but we know that because of some sort of general relativity, we should be able to put, like if you have some sort of well-defined field theory, we must be able to put it on an arbitrary manifold, and this arbitrary manifold can have non-trivial topology, and we can capture some properties of the series in terms of how these kinds of observables depend on the topology of the space-time. Yeah, we'll usually, if we talk about kind of space-time, we usually use for the space-time manifold. We'll usually use a notation M. What else can we have? Well, if you have some, we can have some sort of fields. Let's say classical fields on our space-time, being kind of not just some sort of simple scalar fields or simple Fermat fields, but kind of fields which valued in kind of in some sort of non-trivial topological space X, which is usually called the target space. And in particular, when we have sigma model quantum field series, this is X, or is often considered to be some sort of non-trivial topological space of non-trivial topology. Well, the other topological spaces which can appear is kind of a symmetry group. Can be either global or local symmetry. And of course, this space has more structure than just a topological space, which has a group structure. But sometimes in some questions, as we will see, the topology of this group kind of plays an important role. And another thing which we can consider is kind of when we kind of look at kind of quantum field theory, from the kind of top-down point of view, so we consider all possible quantum field theories, and we can consider kind of a space of this quantum field theories. And we usually want to kind of consider some sort of framework, like all possible quantum field series which have some particular properties. For example, have like a particular dimension and have particular symmetries, maybe anomalies, and so on. With some fixed symmetries. And kind of yeah, this is the kind of yeah, this usually this part is kind of very mathematically quite subtle and not kind of at the moment not super well defined, but kind of heuristically we can consider, yeah, this what kind of the topology is given by kind of saying that the kind of the two series are kind of very close. We can deform one to each another. For example, like slightly deforming some coupling parameters. You know, like for example, we have series with a Lagrangian description. We can deform some couplings. And one might be interested studying topology of this kind of space of quantum field series, and there are examples where these spaces form non-trivial this kind of space of QFTs has non-trivial topology. And okay, when we consider these topological spaces, kind of algebraic topology machinery gives us some sort of again, some sort of algebraic object, for example, a group, associated to this space. And physically, it has a meaning of, can have a kind of different meaning depending on which context we consider it. It have a meaning kind of some sort of describes degrees of freedom. Now here, or it's kind of, or it's myself of kind of classifying different series. And or it can be understood as some sort of space where observables are bounded. So this is the part about motivation. Are there any questions?
No, so far. There are some of them, but they have already been answered by other students in the chat.
Okay.
Oh, there's one.
Is it like visible what how I write? Or is there any?
Yeah, I can see. It's okay. Okay, yes. Yeah, people say it's a little clear. Yes. Yeah, if any has any question, they can also raise their hand and ask directly. That would be nice.
Yeah, unfortunately, yeah, chat. I cannot follow chat.
Oh, there is a question. When you talk about the space of theories, are you talking about GR flows, moduli spaces?
Well, in particular, yeah, what GR flows in particular can be some sort of is a pass, should be kind of continuous pass in the space of series. Yes, this is example. In particular, yes, if you kind of yeah, but it can be some sort of we can consider other type of deformations, not just kind of not just along the GR flow. So you mean like normalization group flow, right?
Let's wait for the answer. Somebody also asked, what is the space of QFTs? Yes, renormalization group says the previous answer.
Okay. So
And the other question is, what is the space of QFTs?
Well, in principle, one way to define it is that, like, okay, when we define a set as a set, well, there's some axiomatic definitions of quantum field series. Well, there are various ways to define it axiomatically, like, for example, basically, yeah, for example, this kind of using some sort of, in terms of, again, algebra of observables and some consistency conditions. And then, of course, there is a question of how to define this like actually topology on this set. And yeah, this is I don't think this is at the moment mathematically like in general, mathematically well-defined. What was kind of defined? It is well-defined mathematically, but there are some particular like cases for example, quantum mechanics. One can do some definition in two-dimensional. For the two-dimensional series, one can do some definition.
Okay, great. There's no any other question for now.
Informally, it's yeah, you allow kind of to you define kind of topology if you can introduce kind of deform there is kind of deform one kind of quantum field theory to another. There's some sort of continuum, whatever it means, continuum family of quantum field series. It means that like all correlators. There's again one parameter of quantum field theory that like that all correlators, all partition, all observables, they continuously depend on this parameter. At least this way we can kind of consider this notion of like continuous paths in quantum field theory. You continue kind of paths in the space of quantum field theories, and then we can ask a question something like fundamental, like considering some algebraic topology those questions. But the short answer is actually not defined, and actually I'm not gonna talk about this part. Yeah, maybe at the very end, as I mentioned about this relation to AO series, and maybe at the very end of the process. But it's not a main part of the course. So you shouldn't be too worried about it. Okay, should I continue? Okay, the next part, yeah, as I expect there are many kind of people with kind of physics background, many students with physics background, so I will have to, so I think it should be useful to review some basic algebraic topology concepts like homotopy and homology and homology in very informal way, so that there are no kind of confusion later on, kind of what things we are talking about. Okay. And so we consider a kind of, when we talk about maps between topological spaces, they understood understood as continuous by default. And to talk about maps between smooth manifold, these maps are understood as smooth maps by default. Okay, so one of the basic notion kind of in algebraic topology is homotopy. So we can consider two pair of maps F and G from topological space X to topological space Y. And we say that they're homotopic. We used a function, continuous function f from an interval times x to y, such that f restricted to 0 gives me f, and f restricted to 1 gives me g. And this is kind of so this kind of parameter value in this interval can be assumed as a deformation parameter, which kind of deforms f to g informally, and this forms an equivalence relation with space of functions. And, so basic example x is Euclidean space and y is another Euclidean space. Actually, any function f x and y is homotopic to just a zero function. a constant function 0, and we just say that the homotopy f is given by the following. So f of t, so t is the element of the interval, is just t times f of x. And this kind of, when t equals 1, this gives me f of x, and when t equals 0, it gives me 0, and this is continuous. So you see, if kind of if the spaces are like linear spaces, so we cannot get any kind of, if you consider homotopy class of functions, there is nothing there. There's only one homotopy class functions. Of course, the basic non-trivial example is that, well, let's say non-example, in the sense that if we now consider x to be R mod z, which is a circle, and y to be also a copy of R mod z, then we can consider a map, which is identity map. And this is non-homotopic. It's not homotopic to a map which is constant 0. And we can think about it and see that it's not a homotopic. So you cannot deform a map which go like an identity map which takes S1 to S1. We cannot deform it to 0. And well, the idea is somehow to kind of to quantify this type of equivalence relation. But before doing this, another important definition is that it's a homotopy equivalence between topological spaces. So pair topological spaces are called homotopy equivalent. By definition, there exists a pair of maps F and G, so that F is a map from X to Y, and G is a map Y to X, such that if you consider composition of G and F, this is must be homotopic to identity on Y, and if you consider composition is the other way around, this is homotopic to identity on X. Kind of these maps don't have inverse, but they have kind of they have inverse up to homotopy there. And in particular, we see that it's obvious that if X is homeomorphic to Y, right, which means that there exists a continuous kind of continuous map which is invertible and inverse is continuous. This will definitely imply their homotopy equivalent, because here is just equality, right? And of course, if the maps are equal, they are automatically homotopic to each other. But inverse is not always searchable. And so in particular, n-dimensional disk, it is homotopy equivalent to a point, but they are, of course, not homomorphic for n greater than 0, just because this is a kind of spaces of different dimension. And in particular, yeah, the kind of algebraic topology kind of usually kind of distinguish spaces only up to homotopy equivalence, which is kind of more kind of rough kind of information about the topological space. So we allow kind of not just kind of homomorphism, but we are kind of allow some sort of more drastic kind of deformations. Okay, any questions?
So far, no. But maybe you can mention a good reference where people can read about homotopy.
Well, the basic reference about algebraic topology is Hatcher's book. It's available online on the author's website.
Okay, great. There's no any other question.
Is it about these questions about these basic definitions? No. Yeah, sometimes it's useful to consider not just kind of topological spaces, but what is called pointed topological spaces, which kind of have topological space and a bit of extra data, mainly the pairs x, capital X, small x, where x is a topological space and small x is a particular element, a particular distinguished element of this topological space. And then we talk about maps between pairs of these pointed topological spaces. What we mean is the following. We mean, we have a map of this. So this kind of contains the following data. So we have a map F, the usual continuous map from X to Y, but we require that the image of this distinguished point in X coincide with the distinguished point in Y. And yeah, we'll see in a moment why this is kind of useful notion. And but before doing that, one can we can also extend the notion of homotopy to the case of maps between points in topological spaces. So we say a pair of two maps F and G from pointed space X to pointed space Y are homotopic to each other if, well, as before, kind of we have as before F is a continuous function from interval times X to Y, such that F restricted to 0 is F and F restricted to 1 is G. But we require, in addition, that for any value of the deformation parameter, this is equal to the value of small f on the distinguished point, which is what? Well, this is f of x, and this is the same as the g of x, right? Because they're both. We kind of you can understand that you have more. Understand that there's some sort of space x, space y, some sort of distinguished point x, here distinguished point y. We study with maps f and g. So this point is sent to this y, and we have kind of one parameter family of maps, but kind of at each value parameter, this x is still sent to y. To this, Then we consider kind of homotopy classes. Maps. From X to Y, and this is denoted by kind of square bracket of spaces. And well, the set is defined as a kind of a set of all maps modulo equivalence relation provided by this by the homology. And in particular, we can define nth homotopy group of x comma x by considering the following. So denoted by Pm of x comma x. And we can define it. Well, first we define it as a set, as taking one of these spaces here to be n-dimensional sphere with some kind of distinguished point, doesn't matter which I denote by star. So we can accommodate the class of map from a sphere to our space X. But what's nice about it is this space has natural group structure. So let us, so suppose we have a pair of maps Fg from n-dimensional sphere with a distinguished point to X, distinguished point small x, and we want to define the composition of the homotopy classes of these maps. And it's this will define this is group structure for n, which is called nth homotopy group. The class of a third map, which is f.g, and that's obtained by some sort of concatenation of these pair of maps. So how does it work? So we started. We have started with a pair of maps f and g. So f was kind of a map defined on Sm with some distinguished point. So, and we also had G, which is defined on another copy. Another copy of series. Now the first step is to understand this. We can understand this the n-dimensional sphere as an n-dimensional disk, where all the boundary is glued to one point, and we can make this one point to be exactly the distinguished point issue. So we have this f defined. We can send this f to be defined on an n-dimensional disk where all the points are the boundary identified. And the same thing for G. We understand again. We understand this n-dimensional sphere as n-dimensional disk with bounded points. So here, of course, I'm drawing a picture for n equals 2, but you should imagine this in n dimension. And yeah, the next step is we basically glue. We want to glue these two disks together to get a new n-dimensional sphere. Where all these and the equator of this sphere is again identified to one point. Well, you can here, no, sorry, here it's not identified one point, but it's kind of yeah, this the points which were identified. Now we kind of say that it's they form this equator. This will just mean that this kind of, so we define a new map on one-dimensional sphere, so that on one hemisphere it's equal to F, and the other hemisphere it's equal to G. And of course, all these yeah, all these the points on the equator, they all have the same values, but it's okay. And we can choose actually our new distinguished point on the sphere as any point on this equator. Doesn't matter. We can choose points. So this defines it's kind of a way to understand how this defines this concatenation. This gives me a group structure, and it's easy to argue that this is for like n greater than 1. This is always actually will be a Billinger group. One can always play about with it a bit and see that one can order kind of exchange this F and G without changing homotopy class for this map. And well, for when n equals 1, this group is known as fundamental group. X is marked point. Questions?
So far, there's no question.
Okay. Okay, maybe to make it kind of okay. Again, yeah, I warned you, like in the beginning, I will have to, this will be basically some introduction to some necessary mathematics, but even let me still kind of give some sort of physically motivated example.
There is someone asking, do we suppose that f of x is Sn? If f of s is the n sphere. That's the question.
F of x. So no, well, F was a map from Sn to X. So this is yeah, X. Sn is a domain and X is a coordinate. Also G. Well, we don't, and well, we can ask a question about the other way around. If the image is the whole X, but this is not necessarily true. Yeah, this is not necessary.
And there is another question that say, can you repeat how?
So you can just constant map, all here just maps to one point.
Yeah, sorry for interrupting. There is another question. Can you repeat how to identify the sphere fixing point with the semi-sphere?
Why the sphere fixing point? Well, I can repeat. Yeah. Well, so first, I mean, we use a statement that n-dimensional sphere is a n-dimensional disk, where the kind of all boundary points are identified. And well, more we can consider this as a pointed space where so we consider some kind of quotient topology here, where we identify all points in this boundary, and this distinguished point is a class of this boundary. So again, S1 we understand as one-dimensional disk, which is an interval with these two boundary points that are glued together. So this looks like this. And S2 is a two-dimensional disk, which is the standard disk with a boundary circle glued to one point. So this is you see sphere with one. Okay.
There is another question. Does the definition of the fundamental group depend on the fixed point X in
Yes.
capital X?
Short answer is yes. The long answer is that it depends up to isomorphism. It only depends on the image in the kind of it's only okay if this Borel space is connected, it's independent up to isomorphism on the choice of distribution. If X if X is connected, well, what's connected? It means that well, this is pi 1 of X. Let's say X is isomorphic to pi 1 X prime to choose some other point. But this isomorphism in general is not canonical. It's isomorphic, but there's a choice of how we do this isomorphism, and it's there's no kind of in general there's no natural choice. And if well, in general, for if X is a disjoint union of class components, class connected components, well, we kind of this the fundamental group is coincides this fundamental group of just a class connected component Xi, where such that the class connected component which contains our marked point. And the same is true for higher fractal groups. Does it answer the question?
Okay, it seems everything is fine.
Okay, some other questions?
Oh, I think there is one. How is defined FG, the map?
Well, this this is what I tried to informally explain. I mean, I didn't give a very precise definition. I just tried to explain this kind of geometrically, but maybe there is some particular part of what I said which should be elaborated. Yeah, I mean, what I explained is that we basically put the idea is that we well, sometimes one considers instead of kind of yeah, the idea that okay, the idea is to kind of to put kind of on half of sphere F and on the other half of the G, and this will define a new map from sphere to kind of short space like this.
Okay, it seems it's clear. He said thank you.
And of course, one had to work a little bit to show that like all the group axioms are indeed satisfied, and so there is this and inverse. And inverse basically correspond to kind of defining map with kind of changing orientation. And one has to check associativity and so on, but this can be done. And the identity, of course, identity is given by a constant map. So identity by n x, it's represented, it's a class of kind of a map which sends so okay, it's a map from Sn point to x, which is such that f of any let's say y is just given by this. So all sphere goes to just to this mark point. This represents an limit. Okay, let me so that it's not yeah. Let me, since it's algebraic topology in physics, let me give some brief example related to physics. Okay, maybe before that I also mentioned the following remark. So to consider kind of homotopy classes of maps just between topological spaces, not pointed topological spaces, and we consider S1, and when this X is connected, this is the same as a kind of fundamental group of X for any marked point divided by the conjugacy equivalence, but divided by conjugate. So it's equal to conjugacy classes, this kind of homotopy group. Sorry, the set of homotopy classes is equal to a set of conjugacy classes. If you forget about this mark. But in particular, if in the case of this group with abelian, the set of conjugacy classes is the same as the set of group elements of the group. So it's so basically then forgetting about mark point and consider homotopy without mark point doesn't do anything. It's, well, again, anyway, the most important, probably one of the standard and important examples is the homotopy fundamental group of circle. Very often, since after isomorphism, as I mentioned, after isomorphism, the fundamental groups doesn't depend on the choice of mark point. People will often omit explicit choice of this mark point. And this is generated by identity map. Since here we're concerned about maps from S1 to S1, this is generated by the class of identity. And how, for example, this appears in physics, this has a relation to quantization of magnetic flux. Flux in V1 H theory. Sometimes known as Maxwell theory. So what does it mean? So we have well, physically A is U1 gauge field. So it's one form. So if we kind of in local coordinates, we can write it as in terms of component A mu dx mu. So A mu is a vector potential. Mathematically, A is a connection, one form on the one principal bundle.
There is a question. It says, sorry, can you explain why the first fundamental group of S1 is homeomorphic to the integers? But I think the question is to explain the geometric.
Well, geometrically, it's basically, so we have a map from S1 to S1. And okay, there is also a kind of the fixed map point. So this point should go to itself, and it basically works. So okay, we consider and while we can consider different values go around this circle and consider different values. When we go around the circle, we will have a kind of we will create some sort of path. My goals like this, and it will wind certain number of times around this target circle. And this number of this winding number is this integer, which completely describes the class. So in particular, so winding number is a class, and this is the class of F in by one. So again, if S is we realize it as S R divided by Z. So what is the winding number? So it's easy to define if we assume that F is kind of assume that F is differentiable. Which is not necessary in principle. We also only need to be considered kind of only need to be continued. But if it's F is differential, this winding number can also be understood as integral of D. I'm not sure this is well. Let me. Yeah, I'm not sure. This makes sense. What I wrote. But again, well, geometrically, yeah, this is not really geometrically. So if yeah, well, the point here is that the DF, I mean, DF is well defined one form which we can integrate over this. But again, intuitively, again, you go around this kind of around the circle, and the kind of the values of F, they make some sort of pass here, and we kind of count the total number of kind of we count with signs how many kind of full circles we made. You can also understand this kind of in this way. So you have a value of this kind of S. So we understand the kind of the interval 0, 1 with endpoints identified, and then kind of you the other S1 is the other interval, and you can always you're going to send this you will leave the map to the map to R, and then this map will look something like this. And basically, we need to get this integer. We need to count this number. It intersects this plus minus sign is the number which intersects kind of the lines correspond to integer lines. So over here, it is 3. +1, +1, -1, plus. So, you know, it's makes things more clear or less clear. Okay, so we started working. Yeah, we started considering this kind of Maxwell theory. And well, we can consider a particular case when we have some sort of magnetic flux through some two-dimensional sphere, which is in a kind of some two-dimensional sphere in our spacetime. Here we don't really care, like this spacetime can be kind of four-dimensional or not, and that would really matter. Okay, and then we so we can define. So here the point will be that this A might not be defined globally, but the field strengths yeah, the A. So it's again here I understand is a true form. So it's a physical quantity that's always must be always globally defined. Might be always globally defined in our space-time, and in particular, its restriction of this truth here must be well defined. Okay, but then suppose we want to calculate this for the magnetic flux. Through S2. Well, by definition, yeah, if we write it in terms of differential form, this is the integral of, well, maybe up to some normalization, but this is the integral of this true form over this true sphere. And okay, this two-dimensional sphere can be understood as a union of kind of north hemisphere and the southern hemisphere, which they overlap along the equator. And well, there is a statement which I'm not going to probably elaborate on, but if you have some sort of contractible space like a disk, so on this space you can always on this kind of space you can always globally define. On this subspace we can define on it we can define the gauge field. So here we will have gauge field AM, and here we'll have gauge field defined gauge field AS. Okay, and we can well, the integral over S2 it can be understood as a union as a kind of sum of integrals over north hemisphere. And for the north hemisphere, we can use our this potential AM, potential AM, and on the southern hemisphere, we can use AS. Then we can use a Stokes theorem because this is d of something, right? You can use the Stokes theorem to reduce it to the integral over the boundary, and the boundary is of the both of north and southern hemisphere is this equator S1. We have to be careful with the signs because it's kind of which correspond to kind of orientation. So one is careful with the sign, we will see that this will be a difference between integral over equator of this kind of vector potential defined on the north hemisphere minus integral of the same equator of the vector potential defined on the southern hemisphere. So this is the standard Stokes theorem and the theory of differential forms. But then this can be rewritten as a difference. Over difference. But here we know that well the kind of we know that we can have a when we have a kind of two different gauge fields which represent the same physical kind of field configurations, they might differ by the gauge transformation. And we know that the gauge transformation for has this form. Let me write it in this way, where G is well, maybe you something like often this is written in terms of G equals e to the IF, and this is becomes proportional just to the F. But in this way, we actually should write it in this way, because this is the correct way to do it, and where G is a function valued in my gauge group, which is U1. Well, here we can consider restriction, and we're only interested on this on the restriction of this function on this equator. And the equator will be a function from S1 to my gauge group, right? Okay, and so then this is integral of S1 equator, G. And this is actually exactly the winding number, which we talked about, equals to, well, up to 2 pi r. Well, yes, up to 2 pi, because it's 2 pi times n, where n is an integer. N can be understood as a class of this gauge transformation restricted on the equator in the fundamental group y1 of S1, because U1 is the same as S1 topology. So we arrive at the conclusion that the magnetic flux up to some overall constant must be integer. So this is context. And here, what was important is kind of, if we backtrack a little bit, what was important is a fundamental group of our gauge symmetry group. Questions?
There is one they ask what we can define gauge fields on the hemisphere.
Yeah, I didn't. I skipped this part. well, in mathematics, from the kind of in mathematics, there's a general statement that you can always, if it's a contractible space, you can always serialize principle, like serialize a bundle over this contractible space, and it will follow from this general statement. But okay, I can let me try to think if it's some more. Yeah, I'm not so sure I can come up with kind of a very short, simple explanation. But I mean, very roughly, if kind of, we can kind of, yeah, if the space is kind of topologically trivial, then kind of we can. Yeah, there's kind of nothing prevents me to do it to do it globally.
There is another question, but maybe you read it because it's a little bit long. Sorry, can we argue that G as the first Chern class of a bundle and then come to the conclusion that this is why it is quantized?
Well, here I mean, if we know the theory of Chern classes, yes, we can derive that this is quantized, but we have to, well, there's actually, there will be many non-trivial steps, right? So first we need to we'll talk about this kind of characteristic classes a little bit later. But so far, yeah, I mean, we have to define what is these kind of characteristic classes in actually integer homology. And then we have to say that this, but then one has to also kind of use Chern-Weil theory to define characteristic classes in the Rampe homology, and then this we use the F. This F is basically a representative of the first Chern class defined by Chern-Weil theory in the Rampe homology, and then you have to use kind of the fact that this Chern class defined in the Rampe homology is image of the Chern class defined in integer homology, and that's why it has integral periods. So one can use it, but it's it will require a lot of other statements. You know.
Okay, good.
Yeah, in a sense, this is some sort of rough exercise this is some sort of informal way to show that the Chern class integrals over Chern class are actually quantized. Because a priori, if we just define Chern classes in the Rampe homology, they are not obvious. It's not obvious that they have integral values of the integrals of two cycles. But we will talk a little bit about Chern classes. Any other question? How the difference is the G inverse? It's again by definition of the gauge transformation. So, and we know that they must differ by gauge transformation, right? We have like on some sort of subspace, we have two gauge fields which describe physically the same configuration, particularly they have the same field strengths. They might differ by gauge transformation, and this fact. Yeah, this is a fact from gauge theory. Okay. Let me also mention kind of with less details. Similarly, one can consider kind of quantization of instanton number or SU2 H field. So we can have this type of setup in SU2 Young-Mills theory in 4 dimensions. And here we integrate. Now we have a kind of SU2 gauge theory. We can consider individual trace F with F over some, let's say, 4-dimensional, sphere for simplicity. And we can do the same trick. We can split it into kind of northern and southern hemispheres, which are now 4-dimensional balls or disks, and this equator is a 3-dimensional sphere. And one do basically essentially the same argument, and one can argue that it's 8 pi square times n, where n is integer, and it has a meaning of a class of the gauge transformation restricted on this 3-dimensional sphere equator. So this is gauge transformation restricted on this equator is a map from 3 sphere to our gauge group, which now SU2 instead of U1. And we know that topologically group SU2 is the same actually as 3-dimensional sphere. So this class can be understood as a class of pi 3, the third homotopy group of S3. And this kind of the nth homotopy group of n-dimensional sphere is always has that, and it's again generated by an entity. Just identity. Otherwise, the argument is the same. We just take the same trick. And we also use the fact that, the fact which I didn't really explain, that whenever we have on a ball, which is a contractible space, we can always have a globally defined gauge field. Okay, another example is consider fundamental group of SON, which can be understood as a group of rotations of Euclidean space, and this is for n strictly greater than 2. This is known to be the 2 cyclic group of 2 elements, and this has when we interpret this as some sort of the group of rotations for Euclidean space-time. This is 2 Euclidean space, let's say space. This group without time. For time, we usually physically we need to consider Lorentzian group, but unless we do something. And this Z2 has meaning of fermion parity. So in particular, what happens? So we have this group SUN, and we can consider its double color, which is known as spin N group. And this well, this is also happens to be what is called universal, and This Z2 can be understood also as a kind of subgroup of this spin group, such that if a quotient over this Z2, we get back assuming. And so we know that in physics, they actually, like physical states, they actually form projective representation of our symmetries. And kind of, we say that projective representations of SN, they're the same as usual representations of this Z2 subgroup. It's a subgroup which acts not trivially on fermionic states, but not trivially on all bosonic states. Questions?
No, so far.
Okay, let me proceed with some sort of mathematics. Let's consider singular homology. We'll briefly review the definition of singular homology groups. And we start with what is known as group of singular chains in X, some topological space. And we will consider group with coefficients in G, which we assume to be a abelian group. So what is the group of singular chains in X with coefficient in G is defined as follows. So it's a group of formal linear combinations and formal finite sums of this form, where n alpha times alpha, where alpha is considered a map from n simplex, which I explain briefly what this, if you don't know. So this is n simplex for topological space X. And the coefficients in these linear combinations are elements in the abelian, is our chosen abelian group G. This kind of the sum means finite, means that only a finite number of these coefficients is non-zero. Of course, they are kind of usually there are infinitely many possible continuous maps from any simplex to X. So it could be a very crazy thing, but we only consider kind of finite sum where elements, the coefficients are elements of this group. And of course, it has a natural abelian group structure. The abelian group automatically, because we can naturally add up these two formal sums to get a new formal sum. But if we happen to have in two formal, in these two sums, we happen to have to the same alpha, then we just add up coefficients in front of this same alpha using the group law in our group G.
Sorry, I have a question. Maybe my question is a bit back. Sorry, but it took me some time to process it. My question is the following, like, can you maybe explain the short exact sequence that you previously wrote in terms of the kernels and images? Because like, well, I cannot see it immediately.
Okay. Okay. What I wrote was it for spin and
Mm-hmm. Yes.
so well, it depends what. So we kind of we define span as a double cover. And yeah, let's this. So we are again. Formally, we can understand kind of let me like, schematically picture S line like this, and then double cover something like this. So at each point, like we have over each point of Sn, we have 2 points. For each element, we have these 2 points. In particular, we can consider identity inside Sn, and these 2 points which cover the identity element, they form this Z2 subgroup. So the sequence is exact because well, first this is the injective map, and well, this is a subjective map because it's color, right? And well, we see exactly that the image, well, the well, by kind of this means that the kernel is exactly this Z2 sum. So the kernel of this map is the image of this. And so it's also could be instructive to keep in mind example when n equals 3. We have spin 3 is the same as SU2 familiar group, and SO3. Well, SO3 is SO3, but it can be understood as SU2 quotient by the center of subgroup Z2. Right? This is the Z2 inside SU2. We have a subgroup given by identity matrix and minus identity matrix. And here, and geometrically, as we already considered, SU2 is understood as a three-dimensional sphere, and SO3 is understood as a real projective space, which is S3 quotient by equivalence relation, which identified antipodal points. Yeah, to summarize, the exactness follows from if I define spin n as a kind of as a double cover of Sn or Sn. Well, first of all, I should define this as a non-trivial double cover. Okay, for any double cover, this would be exact sequence, but this is a sequence which does not split. Of course, in principle, we can consider also something like trivial SON times Z2, but this would be another choice of having a double cover, but this is not what we want. We make another double cover, which we need. I mean, it's one way to define this.
Okay, thanks.
Okay, if there's no more questions for now.
There is another question. Yeah, there is a comment in chat. Indeed, it's also can be considered kind of in this case, it's also universal cover. So they always kind of if you start with yeah, there always a sequence of this mentioned. Well, it's written as this kind of fundamental group of the quotient from universal cover.
So actually, there is another question. Is there any reference you are following for algebraic topology in physics?
No.
Okay.
Well, not anything in particular. Well, again, for algebraic topology itself, I can consider like okay, there's a systematic like exponent. Yeah, systematic material by Hatcher change. So, okay, so we yeah, we start defining. Okay, we define this the group of singular chains. Yeah, well, I have to just be sure to mention that what is the M simplex. Well, it's kind of for delta zero is just a 1 point space. The zero simplex. The one simplex is an integral. The two simplex is a triangle. The series simplex is a tetrahedron, and so on. One can give a formal definition, but you can you probably can understand what's happening. Okay. And I consider this boundary homomorphism. Group of singular n chains to this group of singular n minus 1 chains. By default, so we have some formal sum over maps with from n to this x. Application of the bounded noise gives me the following. That I repeat the sum over alpha, but there will be extra sum over kind of index going from 0 to n. And I consider minus 1 to the I and alpha times alpha restricted on the east face of delta. So in particular, so here, of course, if I have something like minus 1 times an alpha, I understand that there's minus an alpha, so this is the inverse of an alpha in my BM. And for my group, I use additive convention. In particular, so for example, if I have something like delta 2, so I have sum from 0 to 2, and this would be, so I consider I have a map alpha defined on this to simplex, and I consider restriction to 3 different one simplices, which form the kind of traces here are edges, and this will constitute my new sum. I start with some sort of formal sum. The important property of this map is that this composition is 0. And if you haven't done this exercise before, you should do this. Then and people often say that if I commit this dependence on X and G, that this kind of sequence of abelian groups, boundary homomorphisms, this forms what is called chain. Here, like this is a particular case. This is a complex of singular chains in logical space X with coefficient G, and then we define homology groups, singular homology groups. The kernel of this hence boundary homomorphism to respect to which is due to this relation, this is a subgroup here. Elements of homology, they kind of equivalence classes can be understood as some sort of elements in CM such that the boundary defined before 0 modular equivalence relations, so that we can add A equivalent to A plus D of something. Add the definition, yes, the definition seems to be quite complicated. And so it's because these the groups of singular chains is usually some very infinitely generated groups. But what one usually does is kind of calculate these groups using some properties. I'm not by definition. So one is important properties is kind of I'm not going to mention all the properties. Contrariety is that if you have a map between topological spaces, between topological space X and Y, this induces some natural map. It's called push forward between the corresponding homology groups. So homology groups. This map is basically so if you have homology class represented by some singular chain. We map it to basically the same singular chain, but we compose alpha. So alpha will map from n simplex to x, and we can compose this alpha cursor with a map to y. This will give a map from delta m to y, and this will define a singular chain in y, and one can check that this is well defined in homology. And using this functionality in particular, one can show that homotopy invariance. So if you have a pair of topological spaces which are homotopy equivalent, so we defined homotopy equivalence as before. They are homology groups. So here, people often omit coefficients if they can fix something. Then the corresponding homology groups are known to be isomorphic. And there are other properties like excision theorem and the fact that this short exact sequence of chain complexities induces long exact sequence of homology group, in particular, like Mayo vectoric sequence and so on. And also one can use the fact that this is the single homology groups are known to be isomorphic to what is called cellular homology groups or simplicial homology groups. And they can be like, if we have some sort of cellular decomposition of our topological space, we can use the decomposition to calculate these groups to just some sort of combinatorial way. Question?
There's no any other questions.
Let me mention some physics intuition, physics or geometric intuition. Actually, let me use, instead of x, let me use, this intuition usually makes sense when m is something like in physics, this intuition makes usually applicable when m is something like space-time manifold. So this kind of, we can understand this Hn as some sort of network and the elements of this Hn group, we can send networks of sort of defects and dimensional defects M violate by elements of G, modular some sort of deformations. So what does this mean? It can be understood as something, what is it? Like network of defects, one can imagine with something like this. So perhaps some sort of this sum representing class in homology. So we can consider something like 1 alpha 2 alpha 3. So this kind of here I mean kind of images. So it's alpha images So here, by kind of alpha, I denote the image, I capture the images of this map from singular and simplex to X. So here, this may be literally, this picture makes sense for n equals 1, where this is kind of images of just intervals. And then I have kind of, I also actually need to choose orientation. And I also need to kind of color each of these guys. Like here, I mean, I explicitly write it on something like this using some index I. Index. I need to color them by some sort of elements of the group. And the fact that there is some sort of formal cycle. So it represents it's a chain which has zero boundary. And correspond to the fact that we have this kind of junctions of these defects like this. There are some sort of conservation laws going on, particularly including some orientations. So particularly at the junction, which should have some acceleration law like this. So this is 0 G. And this happens each conjunction. And now we need to consider this model deformations, meaning that we can kind of move around this network. We can this network a little bit. We can wiggle, and this will correspond to the same homology. And well, one can see that why this is the case. One can see, for example, if I do some deformation like this, these two single chains will differ by the boundary kind of this singular two chain consisting of these three triangles like this. Okay. And of course, yeah, I'm also kind of using this kind of intuition. I'm also, of course, I'm allowed to change orientation on my defects by changing the sign of this group element. Okay, I think we have to stop at 6, right? So